All right. So I mentioned last time that you remember from calculus 1, you have the derivative. Derivative referring to the interpreted as the slope of a tangent line. And if we move up 2 dimensions, instead of a tangent line, we have a tangent plane. That's what we're going to talk about now. And any number of dimensions, the tangent, whatever, tangent line, tangent plane, can give you a simple linear approximation of your function that works well, at least near a point. And these linear approximations are often quite useful because they're so much easier to work with. Now, I'm going a little out of order with respect to the textbook, just because when I first got here 7 years ago, we were using a different textbook, so that's just how I did my notes. So I'm just going with that. But as far as homework problems, I made sure it won't be an issue. So to recap for 1D case, a given function f of x near x naught has this linear approximation and I'm going to use this notation, capital L sub f. So the L means linear, and then whatever function I'm taking the linear approximation of goes here as a subscript. So all we do to get the linear approximation is we plug in x naught into our function first, f of x naught. So that right there, if I were to stop, that would be a constant function approximation instead of a linear function. That would work well at x naught and nowhere else. But then I add on a linear term here to make it a slightly better approximation. I throw an f prime of x naught, that's the slope of a tangent line, as you know from Cal 1, times x minus x naught. So we're seeing the point slope form. So this is also gives you a tangent line. So that is our linear approximation. So here's our function. Here's our point at x naught. And here is our tangent line. And you can see, if you're close enough to x naught, linear approximation is a really good approximation of f of x. Certainly a whole lot easier to work with for whatever problem you're trying to solve. But naturally, once you get too far away from x naught, it's not so useful anymore, unless the function f itself is nearly a linear function. Okay. So the point of today is, how does this carry over to functions of several variables? So I'll start with the simplest, but still multivariable case. So we have a function of 2 variables, z equals f of x, y. So now we have change occurring along two directions, the x direction and the y direction. So the linear approximation, which is now a function of x and y, you can see it's important to, and I'm always going to do this, review of a 1D case, single variable calculus, and then show you multivariable, so you can compare side by side, see how they're similar, so that if you're presented with a problem that has more variables, you can get an idea of how it extrapolates. So now we have our function evaluated at our point. So x naught, y naught is once again our point of tangency. And then we add on a term that corresponds to this. Actually, 2 terms, because we're in 2 dimensions. So you have a partial derivative of f with respect to x evaluated at x naught, y naught. So you could think of this as a slope if you were only looking at what's happening in the x direction, times a change in x. So these two terms are essentially the same. It's just that here it's the whole derivative, here it's only a partial derivative. Now, this would account for a linear approximation if I only care about x. So I'm starting at this point x naught, y naught, and I see what happens. So this will approximate f well if I leave y frozen at y naught and I only vary x. So if I want to account for change in any direction, x or y, I need another term. So based on what I've just written here, what do you think that term should be?
Partial derivative of y with respect to x.
Not y, but f. Yeah. Yeah. Z, your dependent variable. Yeah. Partial of f with respect to y, still evaluated at the same point of tangency, x naught, y naught. So both of these play the same role as this. But now I have a change in f with respect to y times what? Y minus y naught, the change in y. Okay. And you think, here we have, since z is f of xy, this is like dz dx times dx. So you think of a dx as kind of canceling, and that's at least part of a change in z. Here we have dz dy times dy. So, so that's the other part of a change in z. Now, so then what happens is the equation of the tangent plane is, so you can think of it as kind of like point slope form in a way. So I have z minus z naught instead of y minus y naught. Because up here in one-dimensional case, y is a dependent variable, but now it's z. So z minus z naught is equal to, I'll use a shorthand, fx at your point of tangency times x minus x naught plus fy, x naught, y naught, y minus y naught. So this corresponds very closely to how you would write the equation of a tangent line if you did that in point slope form, because that would be y minus y naught equals f prime of x naught times x minus x naught. So it all generalizes in the really most natural way that you could imagine. So if I were to try to draw this, of course this is going to be a pain all semester long trying to draw these things on a two-dimensional board. So it's like, well, how is this different than this? Well, that's a curve, that's a surface. You'll just have to trust me on that. If you'd like, I can try shading it. No, I'm not going to do that. So here's your point. So just go with me on this. This is a three-dimensional thing. And you have this plane. And just as this line is just touching the curve at a single point, this plane is sitting on top of this surface at this single point of tangency. And however the surface is changing as you wander away from this point in either the x direction or y direction, that is the rate of change you see with respect to x or y. And so between the two terms together, that describes the entire plane. And this is similar to the equation of a plane that you would have dealt with in Cal 3. All right. Well, I won't have today be completely devoid of examples, so I'll do an example now of how you would. So given a function f of x, y, z, or just a function however many variables it is, and a point. So those are the two things you need for these linear approximations. You need the function and the point of tangency, because you're only going to approximate f near that point. All right. So we'll do a function of two variables, 2 2x squared y plus 3y squared. Okay, and my point of tangency is 1, 1. And we'll see how, after we construct a linear approximation, we'll try using that to estimate value of f at a point near 1, 1. So, what information do we need? You need a partial derivative, both of them, with respect to x and y. So what are those partial derivatives in this case? So first with respect to x. So y is treated as a constant.
It's going to be 4x, y.
4xy. And then this contributes nothing. And then with respect to y,
Just 2x squared plus 6y.
yeah, because now x is a constant, therefore 2x squared sits there as a constant. And then you're differentiating y with respect to itself, and you get 1. Now, since soon you'll be doing a homework where you're computing lots of partial derivatives, does anyone have any questions about why these are partial derivatives? Now, once you have them, from the equations over there, we plug in the point of tangency. So we need to set x and y equal to 1 in both. So in this case, you're just going to get 4. Oh, that's fx. And then fy, plug in x and y equal to 1 here, so we're going to get 8. So now you can write down the linear approximation. Okay, so what that is that is the, well, first repeating formula. So this is a function at 1, 1 plus fx at 1, 1 times a change in x, which is going to be x minus 1. So whatever your x naught is what you must subtract, plus df dy at 1, 1 times y minus 1. Okay, so that's our template. All I've done so far is fill in, here's what the point of tangency is. And now I've already plugged in 1, 1 into these partial derivatives, so I have that. But I also need to plug 1, 1 into the function. So what is f of 1, 1? What?
5.
Yes, 5. Okay. So now it's filling everything. So now we have 5 plus fx, which is 4, times x minus 1, plus 8 times y minus 1. And if you like, you can expand that out and see if you can simplify that, although it's not necessary. In fact, if we're going to evaluate this at points near 1, 1, it might actually be more convenient to leave it in this form. So what I'm going to do is to show you how this can be used to estimate the value of f at a point near 1, 1. So you wouldn't have to, because this is a particular simple function, but what if a function is much more complicated? The linear approximation is always going to have this nice simple form, no matter what f is. So I'm going to look at f of 1.1, 1.1. So I've wandered away from my point of tangency by 0.1 in each direction. And let's see, so if I plug in these values into f, so that's my exact value, then what I would get is 6.292. But now let's look at the linear approximation evaluated at that same point. So that's going to be 5 plus 4 times the change in x, which is 0.1, plus 8 times the change in y, which is also 0.1. So we get 6.2. So not bad, considering that this is like I said, this is going to be a much simpler function to evaluate generally than what f is going to be. And if you're looking for the ballpark, this is what happens in a lot of applications where working with the original function is too cumbersome for whatever reason, so we use some linear approximation. And so this plays a role, for instance, solving really all kinds of numerical methods, like solving very complicated nonlinear equations or solving differential equations. These linear approximations are used all the time. Okay, but now I'm going to do one more estimation to show you an interesting effect. Because here, I wandered away from my point of tangency by 0.1 in each direction. And in this case, the error, so the exact minus the approximate, was 0.092. Okay, so now I'm going to do it again, except I'm going to stick closer to home. So 1.01. So now I've only wandered away 0.01 in each direction. And let's see what happens. So I plug these into F, I get 5.120902. And then my linear approximation at the same point is going to be, so that'd be 5 plus 4 times 0.01 plus 8 times 0.01. So just like before, just a different step. And you get 5.12. So again, pretty close. So the error this time, if I just subtract these, I get 0.000902. Okay. So here's what's interesting about this. I cut down delta x, delta y, how far I was moving away from point of tangency, by a factor of 10. So from 0.1 to 0.01. But how much roughly did the error reduce? If you look at the error from the first time and then the second time, again, it's not going to be exact, but roughly by what factor was the error reduced?
100.
Yeah, it's always squared. So that's true in general for a linear approximation. So you have at least that measure of accuracy. Because another way to look at it is, this is more relevant for a 1D case because that's what you're used to. In Cal 3, you dealt with Taylor series. And I know that probably is traumatic to some of you, but that tangent line approximation is the first two terms of your Taylor series. And then you leave out all terms after that, starting with a second derivative term, which has a factor of change in x squared. So because that's the first term that's left out, that's why the error behaves that way. It's proportional to that deviation squared. Okay. So in other words, linear approximation, it's a very simple approximation, but it's more accurate than you might expect. Okay. So any question about this example?
As I was writing down, I missed how we got 5. How did we get 5 up there?
Oh, just plugging your point of tangency into a function.
Okay.
Yeah. So yeah, it's because we need to plug in that point of tangency into the function and the derivatives. We need all of that. Okay.
What's it?
Oh, 13.7 in the text. And 1.5 in my notes. So kind of jumping around the chapter, because then we'll go to chain rule in the next section. We move back. Okay. Now, okay, so now I'm going to do another example involving linear approximation to show you one of many applications it can have. Because in many applications, you are taking some sort of measurement and then you're computing something from that measurement. And with measurements, of course, there's uncertainty. There's limitations in whatever you're using, whether it's just a plain old ruler or some very sophisticated electronics. And what you need to know is, if you have an idea of how far off your measurements can be, but then you use that measurement in something else, how far is that going to be thrown up? And you have to be careful because it's easy to have a misconception. You might think, okay, suppose you are measuring some dimensions of an object, and based on your equipment, whatever you're using, you know that you will be off by, say, at most like a millimeter in either direction. Then you plug it into some formula to compute like volume or something like that. You might think, oh, okay, if my dimensions can be off by at most this much, then anything I use them in will also be off by only that much. It doesn't work that way. Errors, very tiny errors, can be amplified. Actually, in one of the other classes I normally teach, Math 460, I talk about this kind of how that kind of error and the failure to take it into account properly can be so disastrous because it actually caused the loss, the deaths of 28 American troops in the 1991 Gulf War, because we weren't careful about how to handle error. So that's beyond the scope of this class as to how that happened. But the point is, these things are real, all too real. So this example will illustrate my point. So formula for volume of a cylinder, pi r squared h. Okay. What? Okay, well, good thing I haven't written down much yet. And I'll probably need to remind me of that. Strange thing is in my other classes, so trust me, nothing against you guys. Actually, yeah, this time we have a few people who may need to actually watch this. Let's suppose you are trying to measure the volume of a cylinder. You have an actual cylinder. So you go ahead and take measurements of the dimensions, the radius and the height. And you find that the radius is 5 centimeters. And I mean, I won't lie, mathematicians genuinely do not care about units. Okay. Now, so if you go ahead and plug these into a formula, and what you get is 250 pi cubic centimeters. So now you want to take into account, like, if these measurements for radius and height are off by a certain amount, how far off might the volume be? So I'm going to make a distinction here between actual error and estimated error. Okay. Now, the actual error in a function z equals f of x, y. And this would apply to any number of variables. So I'll just use this two-dimensional case here. The notation I'll use is like delta z, which would be f of x, y minus f of x naught, y naught. So I need to explain what all these symbols are. So x and y are the exact values of whatever it is. Like in this case, it's like the radius and height. These, x naught, y naught, are the measured values. Okay. But the thing is, if you could compute this true error, you wouldn't really need it because that means you would know the actual values of x and y. You can just plug it into your function and get the exact value of whatever you're after. The point is, this is the idealized version. This is something you want, but you can't get. Because all you can do is, you have a rough idea of the gap between x and x naught, or at least you have an upper bound, like based on the precision of your equipment. But that's all you got. So you have to settle for an estimate of the error. And I'm going to use notation dz for that. This is called a differential. So when I use the d, a plain old d, instead of a delta symbol for change, that's used to refer to a differential. In this case, it's an error estimate. And for this, we can use a linear approximation. So a change in z would be partial of f with respect to x at your measured values times your estimate of a change in x. So this is also differential. We have differentials in x, differentials in y, and z. So independent and dependent variables alike. Plus partial of f with respect to y, evaluated at measured values times dy. So if you have an idea of how far off x and y can be, again like an upper bound, then the partial derivatives can give you an idea as to how much those errors are amplified to estimate the error in z. So in this case, we're going to use, we're going to say here's how far off r and h can be, a radius and height, and use this kind of formula to see how far off a volume can be. All right. So back to our cylinder. If we're going to compute something like this, we need partial derivatives. We need the partial derivative of v with respect to r and v with respect to h. So what are those partial derivatives? So this function with respect to r. So h is a constant. Yeah, so 2 pi rh. Okay. And what about dv dh? So r is a constant now.
Just pi r squared.
Yeah. Okay. So for our error, we're going to assume that the maximum possible error in r and h, our measurements, is both cases 10th of a centimeter. I guess also known as a millimeter. So I want to keep everything consistent with units in centimeters, even though as a mathematician I don't care about units. So now what I can do is write down what dv is. So dv is equal to vr dr plus vh dh. So if the errors in my r and h are 0.1, now the thing is I need to plug in my measurements, my 5 and my 10 centimeters, in here. So I need numbers for these. So I plug in r and h, I get 100 pi for vr, and then for vh I get 25 pi. So filling in all the numbers I have 100 pi times 0.1 plus 25 pi times 0.1. And what you get is 12.5 pi cubic centimeters. So this is a perfect example of how errors can be amplified when you use them in something else. So here we have these only being off by at most a millimeter. And now we're thrown off by, keep in mind that pi is 3.14, etc. So we're talking nearly 40 cubic centimeters off. So that's a lot of amplification. And it's because of these partial derivatives. Notice it's affected by r and h. If I was dealing with a smaller cylinder, then those errors in my measurements would not be amplified as much. So the size of what you're measuring can have an effect. So be careful about that. Actually, there's a whole research area that's relatively new called uncertainty quantification. It's been an oversimplification, but it's meant to try to quantify how much uncertainty there is in any mathematical model. Because, like for instance, in the oil industry, and actually before I came here, I was in the Department of Petroleum Engineering at Stanford instead of a math department. When you're performing some sort of oil recovery operation, there's a lot of mathematical modeling going on to determine how long will the operation take, how long will it take to get out X amount of oil, how much can you expect to extract, etc. And you're boiling it down to these key numbers that management uses to make a decision. But management needs to know how far off those numbers could be, so they can make a more informed decision. It's just like also similar thing in statistics, polls for an election. There's a margin of error, and that should be taken into account too. So trying to get a handle on how much uncertainty there is very important. So any questions about this example with the cylinder? Okay. Now, during the last 10 minutes,
How come on VR, how come we had 100 pi?
Because I have, okay, so 2 pi RH, but so I'm filling in R equal 5 and H equal 10.
Oh, H10, that's right.
Yeah. Okay. All right. Now these examples I've done, we have functions of 2 variables. But if I try to generalize this, it turns out that, okay, so I'll recall this 1D approximation. So if y equals f of x, that means that the linear approximation is f of x naught plus f prime of x naught, x minus x naught. Now, you can imagine, like when I did the 2D approximation, I had 2 terms here, fx and fy, and then you can imagine if I had more variables, like for that homework problem we were dealing with, in a function g of x, y, z, w, I'd have 4 terms. It just keeps getting more and more cumbersome. What if this is a vector valued function, so it gets even worse? But there actually is a way to express linear approximations of a function of any number of variables, inputs and outputs, in a way that closely resembles this, but it requires learning new notation. So I'm going to use these last minutes to introduce that notation, which we're going to use later in the semester, so you have to know it anyway. Because then you can see that ideas from single variable and multivariable calculus are not really as different as they seem. You just have to, I guess, learn the lingo. So now I'll deal with a case, so this is the simplest case, where we have a function f mapping Rn into Rm, like in the first day. If the second day, n inputs and m outputs. So this is the simplest case of your number of inputs and outputs both equal to 1. So now suppose you have n greater than 1, but the number of outputs is still equal to 1. Thank you. So in other words, like for example, W is equal to f of x, y, z. So you have 3 inputs, but you still only have 1 output. So the way you can express a linear approximation of x, where x is now a vector quantity. So x has n coordinates, x1, x2, x3, up to xn. And these could be like, now for a specific number of variables, you can use more intuitive names like xyz or xyzw. However many you have, it is your function evaluated at your point of tangency, which is also a vector value quantity. It has n coordinates. So it's just like this. You plug in your point of tangency. Plus, and I can write this actually as one derivative term, not n. This is the gradient of f evaluated at your point of tangency, dot product with this vector, your x values minus your point of tangency again. So your point of tangency also has n coordinates. I'm just going to use a superscript of 0 here to indicate it corresponds to this point of tangency that I'm labeling x naught. And then we have this beast here, the gradient. What is the gradient? The gradient is a vector, and it contains all the first partial derivatives. So partial of f with respect to x1, with respect to x2. In this case, I'm plugging in the point of tangency. So as an example, we have
Is it a summation of all the?
the dot product will be. But I'll get to that in a moment. Here we have just n coordinates just placed in a vector. So for example, if I have a function f of x, y, z is, well, say x squared plus y cubed plus z to the fourth, then my gradient, because there are 3 inputs, it's a vector with 3 components. Partial with respect to x, which is 2x, partial with respect to y, which is 3y squared, and then partial with respect to z, which is 4z cubed. So you just compute all partial derivatives and you arrange them in order into a vector, and that is your gradient. But, now we'll be seeing much more of a gradient, like really all semester long. But I want to introduce notation here. So this is a vector, and this is a vector. If you have 2 vectors, this is from Cal 3. What is the dot product?
Scalar.
It is a scalar. How do you compute it? So just given 2 vectors, how do you take the dot product of them? So you don't remember that from Cal 3. Yes, that's exactly what you do. So u dot v is u1 v1 plus u2 v2, so on. You multiply corresponding components, as you just said, and add them all up. Okay. So that's what's happening here. Partial with respect to x1 times the change in x1, plus partial with respect to x2 times change in x2, and so forth. So I'll write that out. So this is equal to fx1 delta x1 plus fx2 delta x2, and so forth, up to fxn delta xn, where I'm using this shorthand, like delta xi is the component of x minus the same component of your point of tangency. And if you were to relate this notation like the examples I've done earlier today, you can see how they could be expressed as gradients consisting of, in those examples, it was just 2 components. So anytime you can see this a sum, and you have, in each term you have these 2 entities multiplied together, you can think of it as a dot product of vectors. So that way, if you compare the 2 side by side, they're very similar. It's just that you're using the appropriate multiplication operation. So we just have ordinary multiplication here and a dot product here. And if you have, and I'm about to run out of time, if I have m and n greater than 1, it actually is a very similar thing where f is now a vector valued function, and I have vector f of x naught, and now I would have what's called the Jacobian matrix times a vector x minus x naught. So this is still a vector. This is a matrix consisting of components like partial of the ith component of f differentiated with respect to the j input variable, and we'll have to return to this later, like after I come back. But again, as long as you are using the appropriate multiplication operation for whatever you're using, so here regular multiplication, dot product, matrix vector multiplication, and these are 2 of the special cases of this. You can compactly describe any linear approximation. Now, what I would suggest, now I'm going to ask Dr. Lee to do more examples on Wednesday involving linear approximation, and you can also look at my notes. You'll see in my notes, the examples I did today are from there, but there's additional examples that you can look at. So we're not done with this section yet, but the ball's rolling. So enjoy the long weekend.